Okay, well, I'm what stands between you and a very interesting panel discussion. And so what I thought I would do is try to outline some things that we have been seeing in our research with respect to energy efficiency, both inside and outside the data center. We work most recently on the Internet of Things. We've worked in cloud computing and large-scale high-performance computing for a long time. And what we've noticed is that there's quite a bit of excitement, so much excitement that people have been predicting things like 1 trillion devices connected to the internet by 2025. That should make the people at Juniper Networks a little bit nervous, happy but nervous. And really, realistically, this has not come to pass. These slides are a little bit old, or these things are a little bit old from the internet, maybe 7, 8, 10 years. This was the AI of 2009, 2010, and it hasn't happened. And we're interested in why. Because the idea that the world is completely instrumented and actuatable in an electronic way is a society-changing idea. In the same way that internet search has obviated memory and, in some sense, books, the Internet of Things is really going to enhance senses. You're going to be able to reach out into the environment through the internet and know things through electronic information that you can't know with your senses. So this is potentially game-changing for society, and it isn't really accelerating the way these people thought it would. And here's why. Today, the cloud, which is a huge innovation in computer science, is really designed, the killer app for the cloud is e-commerce. And e-commerce has a very specific architecture. The architecture is that a centralized data repository pushes a great deal of data from the right side of the screen to people on the left side of the screen, largely through browsers and mobile devices. And then a very small amount of data comes back in the form of web clicks. The web clicks carry a great deal of information. The size of the data is not necessarily proportional to the amount of information that they carry. And the order in which the web clicks occur and the timing between them also carry information. But you have a highly engineered architecture that's designed to push great deals of bits right to left and a small number of bits left to right, and then to preserve those small number of bits in large data corpuses so that large amounts of statistics, that's really what this AI stuff is at some level, nonlinear regression, can be applied, and you have reasonable sample sizes in a categorization. That's it. That's e-commerce. That's recommendation engines. That's why Amazon knows what color shoes you want to buy, this kind of thing. The Internet of Things is built backwards. There are lots and lots of things out there, and they're constantly pushing data to someplace, at least in the current architecture. And that data isn't super valuable always. Sometimes it's a series of measurements, and if you drop one, there's another one coming, and you know when it's coming, and it might be coming in 20 milliseconds. So it's really different. The data is not moving from right to left, it's moving from left to right. It's always on, 24/7. It's not intermittent and bursty like shopping traffic. And it's not necessarily the case that it's big data. It's lots of little data. When I open my refrigerator in my home, and that refrigerator opening informs my Nest that it's happened, and some coordination between the room temperature and the refrigerator operation takes place, that's interesting in my home. It's not interesting in Boston. So and that data is not huge, right? The amount of data that I need to do an automated home for my home is not planetary size. There's lots of homes, but it's a really, really different architecture. And my conjecture and our conjecture is the internet's going to have to change, right? What we've got now, which is really architected for the previous slide, isn't going to work for this. Let me show you some data. This is actually from our Smart Farm project. That is a tremendous amount of data to someone who grows citrus, a tremendous amount. You have information about all sorts of environmental conditions. There's information about topology, about soil sediments, so on and so forth. In particular, to make it a little crisper, we're working on frost prevention with these people. And what they're interested in are meteorological conditions at a very small scale. Meteorology is done at a large scale, like zip code scale. They need to know what the temperature is around those fans and near the corners of these growing blocks. And that information is dependent on a great deal of localized data. Let me also point out that this data is nowhere near a data center. This is out in Visalia, California. It's about 4.5 hours from here. There is no good cell coverage out there. There is no internet out there. You cannot trench in this place. You cannot stand up large poles or whatever because it gets in the way of operations. And we need to do computing there. In that setting, power is everything. We do put edge clouds out there. Our edge clouds are not the kind of edge clouds that you put in air-conditioned office buildings. They're the kind of edge clouds you put in powered sheds or hooked up to solar power. And for about $1,000 worth of storage and compute, I need to spend $20,000 on the power infrastructure. So it's 20x more expensive to put the power infrastructure in than it is to put in the computing and the storage necessary to do that application. The power infrastructure you put in is very fragile, right? It's not like the grid. These things are susceptible, usually in California, it's solar, susceptible to dust, sun angle, industrial accidents, bird strike, you name it, we've had to deal with it. Spiders are an issue. So you have a whole set of infrastructure issues. It's invasive. If you really want to do that 20K, there's poles that have to go up, large scale panels that have to be put in certain areas. There are industrial insurance concerns. It's not easy to do, and the scaling properties are terrible out there. That's what the grid has spent 200 years doing, and this is off the grid. So so we've been looking at what we can do about that. Without actually changing the way we generate power. There's lots of smart people who are working on that. We're not that smart. We work on the software. And so we have a new serverless platform of things called Spot. And this was motivated by something that we just heard about in the last talk. What we noticed in the cloud is that a lot of applications are going to functions as a service. This is a model in which it's impossible to create a zombie. You specify a little piece of code. That code gets invoked when an event happens, and then it is uninvoked when the event terminates. So you can't leave something running. It's a great deal more efficient in that regard, and it uses containerization in a great deal more, a lot more efficiently. However, you do have to write in a very specific model, which means your legacy applications are kind of out in the cold. We're a computer scientist at a university. We can rewrite, start with a clean state. So that's what we've done. So we've got this. It's open source. If you're interested, by all means, join and contribute. But the key idea here is that we can write these very, very tiny services, smaller than microservices. We call them nanoservices that run everywhere, and they can be very, very efficient. And so we have an architecture for this. We run edge clouds. And we run them in outbuildings. We run them sometimes in these project containers where we have to bury the batteries underground in case they catch fire. I mean, there's a lot of stuff that we do, but we run these things at the extreme edge. We run the same software on that edge cloud on the devices itself. We run it at UCSB in a regional cloud, and we are going to run this in our experimental data center so that we can study the power and energy requirements end-to-end, and we can run them in the public cloud. And the key thing from a productivity perspective is it's all the same software. We can move things from the public cloud onto the device without modification. What's really interesting about this, though, even though it is so portable, is that it's an order of magnitude more energy efficient than the current IoT solutions. We've looked at all of them. I'm just going to pick on Azure, but we've done this with AWS Lambda and their IoT SDK. What we show here is our methodology and the execution time, and then the energy consumption and the code size for something that goes from the device to the edge. And this is an order of magnitude less energy. And then if you go from device to the cloud, again, an order of magnitude less. That's 10x. Now, we heard about like 2 times better power efficiency. In computer science, you're happy with a 20% improvement. When you get a 10x improvement, there's an awful lot to be done. And this is through software. We haven't done anything to the hardware to make it more energy efficient. If we did that, these numbers get better. So this really shows us why software is an important thing to look at today if we're going to do energy efficiency. And I'll start to wrap up by saying the future of IoT is interesting to us for a bunch of reasons. One, we think high performance computing, which has heretofore taken a back seat to cloud computing and all of the AI that it engenders, is going to make a comeback. It's actually going to be important. And the reason is because with that telemetry data, we are now parameterizing faster than real-time physical simulations of the environment to do things like predict micro winds and heat flux through the tree canopy so that we can do frost prevention. That's a classic HPC problem. It's called computational fluid dynamics, and it needs to be made super energy efficient because we think we can do it on farm because the scale's not that big. We think that the future is going to be a tiered cloud architecture, that you're really going to spread the cloud from the central cloud all the way out to the extreme edge. And you need platforms and energy management and energy efficiency, particularly as you get to where there's no infrastructure, that really dial the energy usage down. And we think that there's a great deal to be done in system software. Yes, new architectures and hardwares matter, and that's all going to make things better, but we can do a lot today, like an order of magnitude better today with software. The last thing I'll say is that this is changing the way computer science is done. PhD students in our labs think they're going to work in a cubicle in front of a screen. Often they need boots, long sleeve shirts, and hats because this takes place out in the wild. But if we're going to do the Internet of Things, and it's not just going to be smart cities, it's not just going to be Los Angeles and New York, this is the future of computer science. I'll stop and say thanks. Point to the smartest graduate students I know, which are the group, the students in our group. They're fantastic. If you're looking to hire the future leaders in tech, these are the people. This is joint work with myself and Dr. Chandra Krintz at UCSB, and I'll stop and take your questions.
Thank you, Rich. So questions for Rich. That was a great talk.
Great talk. I have a question, if you don't mind, Mark.
By all means.
So I really like the smart architecture that you mentioned. So one of the questions there is that if you want to run this sort of nano services, or I call it function as services, close to where the data is, like inside the home, would you consider then changing? And I really like the idea of not having people have to write new code, but to be able to use existing code and port it. But doesn't that require you to sort of assume some kind of near edge kind of a platform that you can deploy at a home or a farm that you're talking about? Because, for example, I think that at every home you have a Comcast router or something like that, which has a x86 typically processor. It could easily be developed as a platform to running some of these your nano services.
That's exactly right.
Okay.
That's exactly what we do. We don't do it on the router yet. We put a small box, or in some cases, a small cluster, which we run cloud software on. We have an emulation for AWS called Eucalyptus, which allows you to just take a small set of computers and turn them into something that'll run AWS images. So we put that in an outbox, and it works with the devices. In particular, if you really want to run things like Python code, let me geek out for a little bit here. If you want to run Python code and you want to run it in something that's got 50 kilobytes of memory, which is what these devices are, you can do this, but you need to run the compiler to generate the bytecode for the Python at the edge on a powered device. So we make these coupled things where there's a platform that's actually part of the deployment engine for the device, but the device itself will run a service. It will export a network connection. We use very, very efficient substitute for TLS so that we're not doing the public key encryption on the device. We do this with a new protocol that uses HMAX, for which there's hardware support in many of these devices. You can really drive all of this down if you start with the premise that you want the device to be efficient. Now, if you start with the premise that you want the cloud to be efficient, you lose all the energy efficiencies at the edge. And so you really need to put that power to optimize at the edge in a platform, as you suggest. Absolutely. All right, what happens if you send live video type of volume data? Does your C-spot platform efficiency there? Yeah, it does, but in a funny way. So we actually have a project called Where's the Bear, where we do this, where there's a very, very bad network link out to an ecological site. But at the ecological site, we've been able to put up enough power infrastructure to do this. And we have an edge device there, and then we have cameras. And we have fairly high power, short distance networking. So the idea is this, we run TensorFlow way out there in the middle of nowhere on this edge cloud. And we capture the images over a short distance with a fairly fast network. And then we classify the images at the edge, and only send the images across the bad network from the road that are important. So, we have something like, I don't know, 70 billion images. It turns out that the yield, the images that are interesting to the scientists who we're working with, is far less than 1/10 of 1%. Most of it is just leaves blowing by camera traps, or trees falling down, or atmospheric conditions triggering an image that isn't useful. If we could do all that classification way out in the middle of nowhere, then we use that link very, very efficiently. Now, it's not a power optimization in that case. We haven't really tried to optimize the power because we had the freedom to put up the infrastructure, but we easily could. So for sure, pushing things to the edge really allows you to do much more efficient long distance communication. And long distance communication is often where the energy goes.
Rich, you mentioned the problem of getting the data back from these remote sites. We should talk more offline, but free space optical communications can certainly deliver 1 to 10 gigabit fairly power effectively and cost effectively, right? You wouldn't need more than a solar panel to drive that, and you'd certainly go 10 kilometers.
Yeah, that's the thing. We're really interested in solutions like that. There are line of sight questions that come up, right? These things grow, and you sometimes got to get above the canopy to get them to get things to work. But we're very, very excited about trying new energy efficient technologies in that space, where the power footprint really dictates what we should do. Like there isn't a huge bandwidth problem for telemetry. There's often a latency problem, right? If you're doing that fan thing and you're actuating the fan, you want the fan to turn on, and more specifically to turn off if someone gets near it, because it's a big dangerous piece of equipment. So you need to respond quickly, but the amount of data you're moving around isn't such that you need high bandwidth, but you do need it to be reliable and low power. So yeah, we're working with folks at IEE. We're interested in things like Li-Fi and maybe free space optical. All these kinds of things would really, really help us. And so that's the future. That's what we're going to do. Other questions I can answer badly. Okay, well, in the interest in keeping us on time, I want to thank you all for letting me speak to you today, and thank our wonderful speakers. They've been fantastic. Now I'm going to turn this over to Tim Sherwood, maybe through Mark Abel, who might have a word or two to say before we transition to our panel. But I want to thank everybody very much for your attention today.